In the first image, that you're looking at the complete PEM electrolyzer system. Ultra-pure water enters from the left after passing through reverse osmosis and EDI purification. Direct current electricity enters from the top. Inside the stack, electrochemical reactions begin separating water molecules into hydrogen and oxygen. Hydrogen exits on the right side as the primary product, while oxygen exits separately as a byproduct stream. At first glance, the machine appears simple. Water in, electricity in, hydrogen out. But hidden inside this stainless steel structure is one of the most advanced electrochemical systems in modern industrial engineering. Every layer inside the stack must maintain stability under pressure, temperature, conductivity control, and continuous electrical load. And this is where the hidden complexity of hydrogen production begins. In the second image, we see why PEM electrolyzers demand ultra-pure water. This is one of the least visible but most critical realities in the hydrogen economy. Even trace contaminants can begin attacking the system from the inside. Dissolved ions can poison catalysts. Silica and organics can foul active surfaces. Conductivity shifts increase resistance inside the stack. And over time, membrane degradation accelerates. The danger is that these failures often happen slowly and invisibly. The electrolyzer may continue operating while efficiency quietly declines, energy demand rises, and maintenance costs increase. This is why the previous water purification systems mattered so much. Reverse osmosis and EDI are not optional accessories. They are survival infrastructure for the electrolyzer itself. Because in PEM electrolysis, purity is not a luxury, it is operational protection. Now in the third image, we move inside the PEM cell itself. This is the heart of electrolysis. On the left side is the anode, where water molecules are oxidized. On the right side is the cathode, where hydrogen gas forms. In the center is the proton exchange membrane, the thin polymer layer that gives PEM technology its name. This membrane allows positively charged hydrogen ions, or protons, to pass through while blocking electrons. The electrons are forced to travel through an external electrical circuit, creating the electrochemical pathway that drives hydrogen production. What makes this image so important is that it reveals the hidden architecture behind electrolysis. The PEM cell is not just a container. It is a carefully engineered electrochemical environment where ion transport, electron flow, gas diffusion, catalyst activity, and membrane stability must remain balanced simultaneously. In the fourth image, we see how electrolysis actually works at the molecular level. Ultra-pure water enters the anode side of the cell. Electricity splits the water molecules into oxygen, electrons, and hydrogen ions. The electrons travel through the external circuit while the hydrogen ions cross through the EPM membrane. On the cathode side, those protons combine with electrons to form hydrogen gas. What looks simple conceptually becomes extremely difficult industrially. Every stage depends on precise membrane conductivity, catalyst activity, water distribution, temperature management, and electrical efficiency. Even small disruptions can begin increasing resistance inside the stack. And this is where the hidden engineering challenge emerges. Green hydrogen is not simply about splitting water. It is about maintaining a highly controlled electrochemical environment continuously at industrial scale. The fifth image shows the hydrogen production flow at the systems level. Ultra-pure water continuously enters the PEM stack, while electricity drives ongoing electrolysis. Hydrogen exits the system and moves toward drying, purification, compression, and storage infrastructure. Oxygen exits separately as a byproduct stream. This image reveals something important about industrial hydrogen systems. They are continuous flow infrastructure. The electrolyzer is not operating in isolation. It is part of a larger industrial ecosystem that includes purification systems, cooling systems, gas handling systems, compression equipment, power electronics, and storage infrastructure. This is why hydrogen projects are so capital-intensive. The visible electrolyzer is only one layer inside a much larger industrial machine. But now we arrive at one of the most important images in this entire series. In the sixth image, we see stack stress and degradation. The hidden reasons electrolyzers fail. High current density accelerates wear. Contamination poisons catalysts. Membranes begin degrading chemically and mechanically over time. Thermal stress damages internal structures. Gas crossover risks increase as membranes weaken. Water management problems create dry spots or flooding conditions inside the stack. And slowly, efficiency declines. This is where the hydrogen economy becomes less about announcements and more about survivability. Because the real competitive edge may ultimately belong not to the company with the largest electrolyzer factory, but to the systems that maintain durability, uptime, and performance under continuous industrial stress. Hidden degradation becomes one of the defining economic realities of green hydrogen infrastructure. In the seventh image, we move into efficiency and energy flow. Every kilowatt entering the electrolyzer matters because not all electrical energy becomes usable hydrogen output. Some energy is lost through electrical resistance. Some is lost through electrochemical overpotentials. Some becomes heat. Additional energy is consumed by water purification systems, cooling systems, compressors, pumps, and auxiliary infrastructure. This is why PEM electrolyzer efficiency becomes one of the most important economic variables in green hydrogen. Even small improvements in efficiency can dramatically affect hydrogen production costs over the lifetime of the plant. And this is where engineering meets economics. The hydrogen economy is ultimately governed not only by chemistry, but by how efficiently entire industrial systems convert electricity into usable molecules. And finally, in the eighth image, the entire industrial ecosystem comes together. Ultra-pure water enters the PEM electrolyzer system. Electricity powers electrolysis. Hydrogen exits toward industrial use, transportation, storage, or chemical production. Oxygen exits as a secondary stream. The system scales from modular stacks to massive industrial facilities. And suddenly the broader picture becomes visible. Green hydrogen is not a single machine. It is an interconnected infrastructure ecosystem involving water purification, electrochemistry, electrical systems, thermal management, gas handling, compression, storage, and industrial integration. The future hydrogen economy will not depend only on producing hydrogen. It will depend on whether these hidden systems can survive economically, operationally, and technologically under real-world industrial conditions. Because behind every kilogram of green hydrogen is an invisible world of precision engineering operating continuously beneath the surface. And the PEM electrolyzer stack sits directly at the center of that hidden world. If you want deeper breakdowns of electrolyzers, industrial hydrogen systems, infrastructure survivability, hidden engineering failures, and the future economics of clean energy, explore H2 Hub by ReneEnergy using the link in the description.